Welcome to UV Physics Academy. So in the last lecture we have discussed about this Simon algorithm, and in this lecture we are discussing some examples. The first one, a 2-qubit example I have taken. The hidden variable s is equal to 3 here. That means 1 1 in the binary notation. So here once again go through this algorithm. Here we have two inputs. Let us say this is x and another one is x XR s, and these two inputs are having a same output. That's it. Okay, right? So here our hidden variable in this example s is equal to 3. Now first let us construct the tabular form. So here 0 XR 3, so there is no common, that's why 3. I have already explained this a decimal state notation, so I request you please watch that earlier class. So 1 XR 3 equal to, here 1 is common in both, that's why cancel 1 and take the remaining, that is a 2. So what does it mean? 0 and 3 have same output, where x and x XR s are having same output. So this 1 and 2 have same output. So that's why the tabular form, this is x and this is f of x. Here we have 0, 1, 2, 3. Now 0 and 3 have same output. Now here don't bother about that output. Let it be some value, let us say a. But a belongs to either 0, 1, 2, 3 something. So 1 and 2 have same output, let us say it's a b. Now that's it, this is the tabular form corresponding to that hidden variable s is equal to 3. Now we have to construct the quantum circuit corresponding to this. Let us, right. So this is the quantum circuit corresponding to 2 qubits. Now here if you see carefully, so we have this inputs 0 0 and 2 head mod gate operations. Here again we have 2 inputs 0, and after that here head mod operations on the first register, and here the second register is measured. And now what about this oracle operation? So this gives, for example, if you have x, here it is a 2 qubits, so a 0, here also it is a 2 qubits, and uf under this operation we will get x f of x, where f of x is the output. Okay, so f of x you can write from the table. Okay, so that I will explain. Okay, so now let us start solving this quantum circuit. Now initially we have this 0, so here 2 head mod operations, that means we can write h tensor 2 operates on this 0, 2 qubits, and here nothing is there, that's why I am taking I tensor 2 operates on a 0. This is nothing but 1 over root 4. So because here it creates a superposition, okay, so superposition of x, where x takes a 0, 1, 2, 3. So that's why this can be written as 0 plus 1 plus 2 plus 3. And here no change as usual, so this is nothing but a 0. Don't forget here 2 qubit string, 2 qubits are there, 0 0. Now here we have this uf operation, so this something oracle function uf. So what it will do? So for example, if you take this is 0 0, that means x 0 will be converted to x f of x. F of x is the output corresponding to x. Now carefully see, here we have, this is a 1 over root 4, and here we have 0, and again here 0, this one. But what is the output corresponding to 0? A. X f of x plus, next x is 1, the corresponding f of x is b. Next x is 2 and the corresponding f of x is b. Please see the table. Next plus 3 and here it is a. Now I can take out common. So this can be written as, if I take a common, 0 plus 3, a plus 1 plus 2. Okay, now here I am taking 1 over, I mean root 2 here by root 2 here, so that's why we can write this is a 1 over root 2 here. That's it. Now if you see carefully, we separated that a second register and a first register. Okay, so this corresponds to second register, this one, and this corresponds to second register. So if I make up some measurement on this second register, I may get this A or B. So for example, if I make some measurement on the second register, and once if I get A, I may get A or B, anything arbitrary. So if I get A, the first register is collapsed to this one. Once I measure the second register, if I get B, then the first register is collapsed to this. Then on that first register, again we have the head mod operations. Okay, so now let us do that. Right, so this is the final result earlier we got. Once again, see here. So once this oracle function is operated, and we got this final answer, this one. Okay, right. Now this is the second register A, and here we have B. So for example, if second register is measured, then we may get either A or B. So I will do for both. Okay, now let us suppose the second register equal to A. Right, so let us suppose the second register is measured and we got A. Then the first register is found in this 0 plus 3 over root 2. Okay, now we have some head mod operations here. So let me talk about this head mod operations. I hope everybody understand this decimal state notation. So here we have two head mod operations, 2 qubits. That's why it is 1 and 2. So here it is H and here it is H. So what are these operations? This is a H of 0 comma 2, and after that you have to add 1 comma 3. Next head mod operation is on 1, that's why H of 0 comma 1, and you have to add 2, that's why 2 comma 3. Right. So the same thing, let me copy here. Right. So this is the head mod operation. Okay. Oh, fine. Now let us operate this head mod operation. On first register. So then what we will get? So first I am operating first head mod operator, any one. Let us suppose operate this H. That means this one. Okay. So here we have 0. So that's why 0 become 0 plus 2. Okay. Plus I am not bothering about the normalization constant. Finally I will write, because here we are just doing the mathematics, right? Okay. Next we have 3, that is on. Here we have 1 and 3. That's why 1 minus 3. That's it. Next, don't bother about that normalization constant. And again we have this one more head mod operation. So the first head mod is H of 0 2, and after that H of 1 comma 3, and the next one is a H of 0 1, and this is a H of 2 comma 3. Okay, so now we have another head mod operation. So let us check. So no need to get tension. You need not to see only 0 plus 2. Anyway, anything you can take combination. So 0 and 1, 0 plus 1. So 0 plus 1, from this head mod operation you will get 0. And the next 2 minus 3 is there. So 2 minus 3 means minus means on. So which is on here 3. So plus 3. So you got 0 plus 3. Okay. So 0 plus 3 earlier itself first register. Now also you got the same thing. That's not a problem. So here we have 2, that's why I can write normalization constant as 2 or 1 over root 2. Now this will give you uh, one is s dot 0 equal to 0, another one is s dot 3 equal to 0. So if I take this s dot 3 equal to 0, here I will get s1 s2 dot 1 1 equal to 0. We can write s1 plus s2 equal to 0, so that implies s1 equal to minus s2. So forget about that phase factor, okay. So this implies s1 equal to minus s2, forget. So if I take s1 as a 0, both will be 0, so that's not the solution. So then let us take s1 equal to 1, then you will get s is equal to 1 1. So no need to consider that minus sign, just leave it. If I take, if I get the second register as a b, let us find this also. Now let second resistor equal to B. Then the first resistor is a collapse to 1 plus 2 by root 2. Now again I am taking this head mod operation. So the first head mod operation, so I hope you understand earlier what we have taken, h of 0 comma 2 and h of 1 comma 3. So 1 it is off, I hope everybody know. First one is off, the second one is on. First one off, second one on, right. So this is a 1 plus 3 plus 2, that is on, that's why 0 minus 2. Okay, next one more head mod operation, so this one, okay. So in this we have the combination 0 plus 1, so 0 plus 1 nothing but off, so here 0 is off, that's why 0. Next minus I have taken common, so then I will get a 2 minus 3, 2 minus 3, minus means on, here on is a 3, so that's why 3, so by root 2. So here also you get the same answer. So anything you can take, only here if you observe carefully, here plus we have, minus we have, that does not matter. So we will get a linearly independent equations, that means s dot 0 equal to 0, this one won't give you, and s dot 3 equal to 0, again this will give you s is equal to 1 1. That's it. Let us take one more example, okay. Right. Now here let us take a 3 qubit example. So here we have taken s is equal to hidden variable as a 6, that is 110. First let us construct the tabular form. So here we have 0 XOR 6, this is nothing but 6. So 0 and 6 are having same output because 6 is the periodicity here. So 1 XOR 6, any common is there? No. 6 is 4 plus 2, 1 is 0 plus 1, that means there is no common, so that's why 7. So 1 and 7 have same output. Next one, 2. 2 XOR 6, okay, 2 XOR 6, what is common? 2 is common, so that's why answer is 4. Cancel the common. Next 3, 3 XOR 6. Here what is common? 2 is common. 3 is a 2 plus 1, 6 is a 4 plus 2, so that's why 2 get cancelled. So 1 plus 4, 5. Right? So if you observe carefully, everything came 0, 1, 2, 3, 4, 5, 6, 7. Okay, right. So let us construct this tabular form. This is x, f of x, input and out. 0, 1, 2, 3, 4, 5, 6, 7. Now here 0 and 6 have same output. So I hope now you understand. I'm just writing it as some a, just decimal state I'm writing a. It may belongs to 0 to 7, any value. So and the next one, 1 and 7 have same, let it be b, and 2 and 2 and 4 have same, 2 and 4, let it be C. Next final 3 and 5 have same, that is a D. Right. Now let us take the quantum circuit. Right. So this is the quantum circuit. Here we have this 3 inputs 0, 0, 0. So 3 head mod gates, and after that this oracle function, and again head mod operations. And the second resistor here, this is the second resistor. Okay, fine. Let us proceed. Now here we have right. So here we have H tensor 3 operates on this 0, and again here identity 0. This is nothing but 1 over root 8. So here we have 0 plus 1 plus 2 plus 3 plus 4 and 5, 6 and 7 superposition state. And after that we have this 0 as it is, and but it is a 3 qubit. Okay, so finally once this oracle operation is done, so what it will do? So 0 and 6 have same output A, next 1 and 7 have same output B, let us suppose, and next 2 and 4 same output, 3 and 5 same output. So now I'm writing that by taking common, I'm writing like that. So then it is a 1 over root 8. So 0 plus a 6 A, next 1 plus a 7 B, plus 2 plus 4 C, plus 3 plus 5 D. Right. Now if I would like to write here root 2, again root 2, here root 2 if I want to write. So this one normalization constant will become 1 over root 4, I mean 1 by root 4, because already you have written, we have taken root 2 here. Fine. So now if I measure this a second register, I may get A, B, C, D. So here don't bother about that second register, you will get some value, so don't forget about it. Okay, you may get definitely either A or B or C or D. So what are A, B, C, D? A, B, C, D again belongs to one of that 0, 1, 2, 3, 4, 5, 6, 7, because we have taken 3 qubits. Okay, so now I can say if second register is measured, so we may get either A or B or C or D. Okay, anything you can take, any value you can take. So I will do for any of two, and the rest of the two things you please try. Okay. Right. So now let us suppose, let second register, once you make a measurement on the second register, we got I'm assuming it as C. Okay, so let it be C. If a second register is C, then the first register is collapsed to 2 plus 4 by root 2. Okay, so let me take that. Then the first register, that is 2 plus 4 by root 2. Now here we have some head mod operation, and don't forget these are 3 qubits, 3 qubit states. Now here we have 3 head mod operations. Okay, so 3 qubits, that's why I can take it as a 1, 2, 4. So let me take this head mod operations here. So this is this. So here we have H, and here H, this is also H. This is 1, 2, 4. So let me take the head mod operations. H of a 0 comma 4, next add 1, that is a 1 comma 5, next again add 2, 2 comma 6, and H of 3 comma 7. Next head mod is on 2, that's why 0 comma 2. How to add 1, 1 comma 3. Next add 4, 4 comma 6 and 5 comma 7. So h of 0 comma 1, so add 2, 2 comma 3. Next add 4, so no need to get tension, it's very easy. So and 6 comma 7. Actually, I mean, instead of doing that algebra, it's very easy to understand the operations, how to operate that gates. That means head mod operations, 3 head mod gates are there. This is easy to do the algebra. Okay, so let us proceed. Now we have first register 2 plus 4 by root 2. Remember, always we have to go from left to right, because these are operations. Okay, first one is a 2, so 2 is off, that's why I will get 2 plus 6. I'm not bothering about that normalization constant, finally I will write. Plus 4 is there, so here is the 4, so which is on, that's why a 0 minus 4. Still not completed. Okay, so again this one here, another head mod operation. So this is the first head mod over and the next head mod operation. Okay, right. So here we have 0 plus 2, carefully see, 0 plus 2, this one. Now we are operating the second one, right. So 0 plus 2, so it's a off state, that's why it is a 0. Next I can take minus common. If I take minus common, 4 minus a 6, 4 minus a 6 here. Okay, so then it is minus common, 4 minus a 6 on, that's why it is 6. Right. Next one more head mod is there, still not completed. Okay, so right. So next head mod, this last one. So we have 0, which gives 0 plus 1 minus a 6, that gives 6 plus 7. So again we have 4 states, that's why I can write 1 by root 4, 0 plus 1 minus 6 minus 7. That's it. Okay, now you will get this, I mean first register we got, once you measure you may get 0, 1, 6, 7. So what I am saying is, if you take any of the second register, okay, you may get any one of that second register, A, B, C, D. Then the corresponding first register if you take and apply the head mod operations, you will get this 0, 1, 6, 7 only. Only the thing is a phase factors change. For example, if you take this first one, you please try this first one, you will get all plus 0 plus 1, 0 plus 1 plus 6 plus 7. Maybe here you will get some other phase changes, but you will get 0, 1, 6, 7 only. So I hope you understand this. Then here I got s dot 0 equal to 0, this one no need to take, and s dot 1 is equal to 0, another one is s dot 6 equal to 0 and s dot 7 equal to 0. So we need to take linearly independent equations, that's why here we have s dot 0 equal to 0 and s dot 7 equal to 0. So don't take these two. Okay, so please take these two equations, s dot 1 equal to 0 and s dot 6 equal to 0. Now let us do this in two different methods. Okay, so I will explain one school level algebra. Okay, so this here we have 3 qubits, so that's why this 1 can be written as s dot 0 0 1 equal to 0, and here s dot, of course s also you can write s1 s2 s3, let me write that also, s1 s2 s3 dot 0 0 1 equal to 0, and the next one s1 s2 s3 dot 1 1 0 equal to 0. This is a school level algebra, easy. Okay, so here we are getting two linear equations. Let me write that. 0 into S1 plus 0 into S2, just I am applying that a dot product, binary dot product, plus 1 into S3 equal to 0. And the next one, 1 into S1 plus 1 into S2 plus 0 into S3 equal to 0. Now whenever you have two linear equations, independent equations, and three variables are there, we can apply this method. But this method is applicable for three variables. If four variables are there, then we can go with the matrix method. Okay, here also you can go with the matrix method. I will explain that also. Here what I am saying is, first write the coefficients, go in order. S1 coefficient 0, S2 coefficient 0, S3 coefficient 1, and again repeat the first coefficient 0. Second equation 1, 1, 0, 1. So this is nothing but what? Here it is a S1 coefficient and S2 coefficient, that's why it is S3. Other than that, S1, S2, what is the other one? S3. Next, S2, S3, what is the other one? S1. Next, automatically here it is S2. That's it. Now you will get S3 by, just take the determinant 0 and this is also 0. S1 by, this is a 0. While you are taking this bottom to top, you have to take minus extra. So that's why this is a minus 1. And S2 by, and here you will get 1 and bottom to top you will get a 0, so that's why here I am taking 1. So finally if you see carefully, we got S1 is, be careful, it's not in the order. So S1, now S1, S2, S3. What is S1? Under S1 we have minus 1, forget about minus 1, and under S2 we have 1, and under S3 we have 0. So that's it. This is 1, 1, 0. If you want, you can proceed with the matrix method also. That I will take another resistor. So let me explain another resistor also, then you will understand. So why they are choosing arbitrarily, let the second resistor maybe A or B or C. Anything you can take, you will get the same answer. That's what I want to say. If you still not understanding, I will take one more example. Okay, right. Let it be D. Okay, let us proceed with the D. So here I am assuming, let second resistor is a D. Then the first resistor will be in a 3 plus 5 superposition state. Okay, like this. Now on this we are operating the first head mod. So 3 become, it is off. That's why it is a 3 plus a 7, no need to get tension, and 5 that is on, that's why 1 minus 5. Okay, if you want to know this method, I request you, there is one video on quantum circuits, how to solve any quantum circuit by using a decimal state notation. See, I'm not doing any new thing, just I'm using this decimal notation to solve the circuit. Finally again I will keep it in the binary notation only, no need to worry. So I'm sure you will get the same answer. So again here I am taking the second head mod. So here little bit careful. So we have 1 and 3 combination, this 1 and 3 combination, and 5 and 7 combination. That's good. So 1 plus 3, that's why off, it is 1. 1 plus 3 off, that's why it is 1. Next minus common, 5 minus 7 on, that's why it is a 7. Okay, again a head mod operation. So here it is a 1, so that's why it is a 0 minus 1, because 1 is on, minus 7, so this is a 6 minus a 7. You got the same, I mean same means some phase changes will be there. So here the first resistor, after operating the head mod operation, we got 0, minus 1, minus a 6, plus a 7, like this. Okay, so here let me take that matrix operation. Okay, so here we have same s dot 1 equal to 0 and this is s dot 6 equal to 0. Because the three variables are there, if you want to solve with by using matrix we need another one also, just I am taking in case. Okay, so here we can write it as s dot 1, that is s dot 0 0 1 equal to 0, s dot 1 1 0 equal to 0. If I want to write it as a matrix, just take the this one 0 0, sorry, yes, these things 0 0 1, next one 1 1 0. I'm taking all ones. Okay, that is a 7, this one I'm taking. So into s1 s2 s3 equal to 0. So finally if you take a first row and this column, you will get s3 equal to 0, it's fixed. Okay, right. And the next one, if you take this a second row and this column, you will get s1 plus s2 equal to 0. So which makes s1 equal to minus s2. I can't take s1 or s2 as a 0 because if I take a 0, all are 0, that's not the solution. So definitely s3 is a 0, s1, s2, s3. So I can take s3 already fixed 0. If I take s2 as a 1, so this is also 1. Forget about this minus factor, like this also we can do. Okay, right. So I hope you understand this Simon algorithm example. I have explained one example on a 2 qubit and another example on this 3 qubits. So I hope you understand this. If you have any doubt, so please inform me. Okay, thank you and we will meet again. In the next video, I will explain this Simon algorithm example in a different way. So without doing all this algebra, we can directly say what are the final output. That means after operating this head mod operations here. So here. So I will say what is the final output. Okay, so without doing this algebra, by using some phase table that I will discuss, that is also quite interesting, but I'm not sure whether it is right or wrong. I'm not sure. Okay, so I request you please watch that next video, it's quite interesting. So we can say these are the final output and these are the linear equations. Okay, so let us hope it may be correct. Okay, so thank you so much and we'll meet again in the next video. Please watch the next video, please.